Markov chain Monte Carlo is an extraordinarily powerful tool for sampling from and computing expectations with respect to very complicated high-dimensional probability distributions. And in fact, MCMC, as we call it, was named one of the top 10 most influential algorithms of the 20th century, at least by the editors of a publication of a journal called Computing in Science and Engineering in the year 2000. So in this video, I'd like to tell you a little bit about the situations in which MCMC is applicable and the intuition for why it works. And then I'd like to briefly tell you about a very intuitive example, which was actually the motivation for one of the original formulations of MCMC called the Metropolis algorithm. So the goal of MCMC, as I was just mentioning, is that we want to sample from some distribution P or approximate an expected value, an expectation, E of f of x for some function f, and f might be a very complicated function, and here this x is distributed maybe according to some complicated distribution P. So the picture is we have some, maybe this is our P, and it's some super complicated probability distribution, and this is notionally, I'm just drawing it as one-dimensional, but notionally this is in some very, very high dimensional space. And then we have some function f maybe in this situation also. And the problem is that this P is just super complicated. So doing this analytically is just out of question. And so we talked about Monte Carlo, just sort of standard, straight up, basic Monte Carlo, which was to, if at least for this part, to approximate this expected value, to do that by computing this sample mean, where these xi's were drawn IID according to this distribution P. Now the problem, well, the first problem that might arise is that this P might be way too complicated to actually sample from. That was the first sort of problem. And so we talked about another way to get around that, which is to do, say, importance sampling was one way to get around that, where you have some proposal distribution Q and then you correct for the fact that you're using the wrong distribution. Or you could do rejection sampling would be another option. But a problem which arises with both of those approaches in very high dimensions is that even a proposal distribution, which might seem just really good, you know, like it just really seems to fit. It's not exactly P, but gosh, it's just close. Our intuition for a good proposal distribution in low, we only have good intuition for low dimensions, 2, 3 dimensions, maybe 4 if you're lucky. But in high dimensions, the problem is that our intuition for volume just breaks down. We just have very poor intuition for volume in high dimensions. And so a proposal distribution in high dimensions that might seem to be a good one can just utterly fail in high dimensions because it ends up putting probability mass, a lot of probability mass, in regions that have very, very low actual probability P. And so your proposal distribution just utterly fails in high dimensions. Oftentimes this happens. It's just difficult or impossible to get a good proposal distribution that you can actually sample from. So the intuition for Markov chain Monte Carlo, at least my intuition for it, is the following. So this is just our notional sort of very high dimensional space here. And the intuition is that this distribution P, distributions like this, the ones that we tend to be interested in at least, they have some sort of structure. They have some sort of regular, well, maybe not very, very regular structure, but they have some, at least some sort of, they tend to be sort of these connected spaces. And they're sort of in sort of a manifold in this high dimensional space. I'm using the word manifold very, very loosely here, not in a rigorous sense. But it's sort of this, I'm drawing sort of the high dimensional, a region of high, not high dimension, of high probability P. Sort of this sort of wispy kind of region, the subset of this very high dimensional space. Maybe it's sort of like this. This is just all completely notional. And so the idea of Markov chain Monte Carlo is that you want to be sampling from this very sort of small subset of this high dimensional region. And so, doing just a very simple sort of thing, if just taking every possible value is just totally out of the question. And constructing a proposal distribution is too hard. So the idea is you just start somewhere. Maybe you start here. And then you start just moving around, and you try to move toward a region of high probability. And then you get there. And then you try to stay in the regions of high probability. So you're sort of doing this random walk, and you're trying to stay near this high probability region. So you're just sort of moving around here and just exploring this space, this high probability subset of this very high dimensional space. So you're just kind of walking around here like this. And you do this by forming a Markov chain. We'll talk more about how that's done in the future. So this is the idea. This is the intuition, my intuition at least, for what MCMC is doing and sort of why it works. And the reason why it works is because you can move around. You can, if you're just sort of staying in this space, then you can hit it with, you can move around in it much more efficiently. You're not like just choosing all these other points that aren't in the space. And of course, the regions of high probability are the ones which make a difference. They're the ones which really count when you're computing this expectation. So it doesn't matter what's going on over here. Okay, so that's the intuition. And let me tell you now about an example of this to sort of make this a little more concrete. And so here's also some pictures of some of the people who were involved in developing MCMC. So it's John von Neumann, who built some of the first computers and developed Monte Carlo methods. Ulam and Metropolis wrote a paper in 1949 that first sort of laid out the idea of using Markov chains for Monte Carlo approximation. And then Rosenbluth and Metropolis and Teller, along with the wives of Rosenbluth and Teller, wrote a paper in 1953 in which they applied Markov chain Monte Carlo to the following problem. So I'm going to tell you about the problem that they applied it to. All right, so here's the problem. Suppose you have, so think about, if you, I don't know if you remember from chemistry, if you took chemistry, you have these phase diagrams. And in a phase diagram, it sort of looks like this. You have this solid region over here of the phase diagram, and then you have a liquid region. And then over here you have a gas region. And this is, on this axis is temperature, and on this axis is pressure. And so, for example, for a material like water, water has a particular phase diagram, and this is of extreme interest to physicists, understanding these phase diagrams for different materials. And so, because this is such a sort of prototypical type of behavior, this sort of phase diagram, they all sort of tend to look the same for just a huge range of materials, water or CO2 or helium, or just a huge range of different substances have a phase diagram that looks very similar. And so as a theoretical model to try to understand this behavior, the following model was proposed. So this sort of hard disks in a box model, as it's called. was proposed, in which you have this box, and then you have these disks, these circles. And these circles they're all the same size, and they're meant to represent individual molecules. And they're bouncing around in this box. They're just all moving all around. And they're called hard disks because they can't overlap. You can't have this situation. And that constraint, so this is a high dimensional space in that if there was n different particles here, then each of them, their x and their y position in this box, those each contribute 2 to the dimension, and so you'd have like the dimension would be something like r to the 2n, or whatever this box to the 2n, something like that, the width of this to the 2n. So it's a high dimensional space when you have lots of particles, when n is big. And it's a complicated space because of that constraint that they can't overlap. So that makes it very complicated. If they could overlap, then everything would be kind of easy. But that hard constraint makes this a very, very complicated space. And so physicists are very, very interested in understanding this theoretical model. And these guys, being physicists, they were interested in understanding it. And so they used Markov chain Monte Carlo to try to simulate this model. And in fact, they were interested in computing expectations. They were interested in computing expectations of this form. And x here would be the state of all of these particles. So the state would be the position. Each of these particles has a position, and x would be the vector that contained the position of all of these different particles. And the idea is very simple. So the idea is that you start out, so we were talking about here, you start out and then you just start moving around. You start moving around and you're exploring the space. And so the space that you're exploring here in this example is the space of all these valid configurations. And it's valid when you can't, when no two of these overlap. That's what I mean by a valid configuration. And so you have to define these moves. Here we were moving around in the space, and the moves that they used were the following. So at each step in in time, you move each of these guys, or you consider a move. So this particle, you would consider a move of the following sort. You take its current position, and then you consider a box. You have some predetermined parameter which determines the width and height of this box. And then you uniformly draw a point in this box. And then, according to a sort of randomized rule, the metropolis rule that we'll talk about, you either accept or reject that proposal. And so if maybe you drew this point and you accepted it, then you would move that guy there. And then you would consider the next guy. And then you might move him here, and then you might move this guy here, and this guy might stay where he is, and then you might move this guy, and this guy might stay where he is, and so on. So updating each of the particles would give you one iteration of the algorithm. And you run that a whole bunch of times, and you compute. So each of those iterations gives you a configuration, xi, and then your approximation is very much like the standard Monte Carlo approximation. You just form this sample mean where each of the xi's is the points, the configurations that you got as you ran this sort of simulation. So it's a very, very sort of intuitive, sort of very understandable idea. And it turns out that even though these xi's are not IID from the true distribution P, that this MCMC estimator is actually a good approximation of the true expectation. oh, I shouldn't be using, sorry, I'm using n for two different things here. This should be, so n here is the number of iterations that we ran it for, and here, n, I was using n for the number of particles, but let's call that maybe capital N. So the number of particles is capital N. And the reason why it turns out that for this problem, and when you have to set it up correctly in order for this to converge to the true thing, in order for it to be a good approximation of the true mean. But the reason why it converges to the true thing is from what's called the ergodic theorem for Markov chains. And we'll take a look at the ergodic theorem for Markov chains shortly in another video. So the reason why MCMC it's possible to even do it on this problem is because we could make these sort of local moves. We could move around easily in this space. And that's what allowed us to do this. So one thing I sort of left out here, I guess, in this description is I didn't say what probability distribution we defined over this x. So x is here is, in order to have an expectation, it has some probability distribution. And it turns out that the probability distribution that they used is what's called the Boltzmann distribution. And I won't go into the details of what that is, but I just wanted to make it clear that there is a probability distribution that they were using, and it's called the Boltzmann distribution for the given, the way that they set up the system. Okay, so I think that's a nice intuitive example to sort of start to get your head wrapped around how MCMC works and what it's doing and what you do with it. And next we'll start to take a more detailed look at why MCMC works.